We studied the transversality of a differentiable map to submanifold in the beginning of the course. Indeed, we saw that transversality is an open property within the framework of monopiece, and Sar's theorem gives a hint that transversality should also be dense. Indeed, we will see that under the right hypothesis, transversality is an open and dense property for the strong topology. Our goal is showing that transversality is an open and dense property for the strong topology. Okay, we are going to introduce first a useful definition. Let F be a C1 map from M to N, and let A be a submanifold of M. Consider a subset K of N. We say that F is transverse to A along K, and we use this notation if the definition of transversality is satisfied for every point x in K. In other words, if the image by the differential of f at the point x plus the tangent space of A at f of x is the tangent space of n at f of x. Okay, we are going to introduce two new notations. The first one is just the space of CR maps such that F is transverse to A along K. And the second one is just for the space of CR maps that are transverse to A along M. In other words, that are transverse to A. Let us introduce the following local transversality result that is a fundamental ingredient in the global transversality results. Okay, let F be a CR map from M to N and consider a closed submanifold A of M. We are going to consider also a compact subset K of M such that the following properties hold. The first one is that K is contained in a domain of a local chart of M. The second property is that the image of K by F is contained in the domain of a local chart of N. And the third property is that the image by the local chart of N of A is actually the submanifold Rk times 0. Under this hypothesis, the theorem says that then the set of CR maps that are transversal to A along K is an open and dense subset of the set of CR maps such that the image of K is contained in W for both the weak and the strong topologies. Let us consider an element G of this set. So we have a map G that is a CR map such that the image of K is contained in W. And now we are going to consider K containing K prime contained in U hat, okay, and contained in U, such that, okay, K prime is compact, K is contained in the interior of K prime, U hat is open, and the image of U hat is contained in W. That is possible by considering a compact neighborhood K prime of K is small enough, and then an open neighborhood U hat of K prime is small enough, okay? Because the image of K by G is contained in W, okay? So we are in this situation. And now we can consider the expression of G in local charts, in the local charts phi and psi. This is a CR map, which is defined in the image by phi of U hat and with values in Rn if small n is the dimension of the target manifold big N. All right? And of course, if we call this G, we can consider two maps, G1 and G2. G1 belongs to RK, sorry, and G2 is going to have values in Rn minus K, right? And we want to know when G is transversal, is transverse to a psi of A along phi of K. Okay, since we are considering local charts now, we have to consider psi of A instead of A and phi of K instead of K. And this is going to happen if and only if for every point X in the image of K, we have one of the following two possibilities. The image of A by psi is the set of points such that this second component is 0. So a possibility is that the image of X by G2 is different than 0. This 0 is the 0 vector of Rn minus K. In that case, no problem. We have transversality at the point X because the image of X does not belong to psi of A. And the other possibility is that the value of G2 at the point X is 0, it's the 0 vector of Rn minus K, and G2 is a submersion at the point X. Okay, with this definition, it is clear that the set of maps actually that satisfy that are transverse to A along K is going to be open. Because if we have a map G that is transverse to psi A along the phi K, okay, what happens is that for all points in the preimage of 0 by G2, we have that G2 is a submersion. And this property obviously holds also true for a neighborhood of this set. And as a consequence, it's also going to hold true for the maps in a neighborhood of G, both in the weak and a strong topology, both in a small neighborhood for the weak topology and a small neighborhood for the strong topology. And so if we have a map that is close to G, either in the weak or to small g, either in the weak or the strong topology, then this local expression is going to be close to capital G, either in the weak or the strong topology. And what we get is that if the initial map was transverse to A along K, then these close maps, these nearby maps, are also transverse to A along K. So what we get in this way is that the set of CR maps such that the image of K is contained in W and G belongs to the space of CR maps that are transverse to A along K, this is an open subset of the space of CR maps such that the image of K is contained in W, right? And what remains to be proved is that the first set is not just an open subset of the second one, but it is a dense subset of the second one, right? So let's see how to prove this. Okay, we have G such that the image of K is containing W, and we can still consider K, K prime, and U hat exactly as before. Okay, and we have this map G, capital G, which is capital G1, capital G2, which is just the local expression of a small g in the charts phi and psi, right? And the issue is that in the points that are in the preimage of the zero vector by G2, G2 is not necessarily a submersion, okay? But something that we can do actually is considering U a regular value of G2. And then we define it's going to be, of course, a point in Rn minus k, and we want a regular value as close to the zero vector as possible. And then we defined Gu as G1, and here G2 minus U. What we have is that Gu is transverse to psi A along phi k by construction, because U is a regular value. And when U tends to 0, these capital G U's are providing approximations of capital G for the weak topology. If we want approximations for the strong topology, we can use the same trick that we have already used to prove the density of embeddings in the space of CR proper maps under certain conditions, right? And this trick is just considering lambda, which is going to be a C infinity map defined in the image of U hat by the local chart phi with values in 0, 1, and such that lambda is equal to 1 in a neighborhood of k, since we are in local charts, in a neighborhood of phi k, and whose support is contained in the image by phi of k prime, right? And then what we can consider, okay, is a map, capital G tilde, okay, which is going to be just 1 minus lambda times G, capital G, plus lambda times capital GU. Okay? And the issue is that, let's write it down here again. What happens is that this map is equal to these two maps. The capital G tilde and the capital G are equal outside the image by phi of k prime, which is a compact set, right? What we have is that when U is a regular value that converge to 0, then capital EU converges to G, to capital G in the weak topology, okay? And when we consider this formula over here, in which independently of U, all the maps that we define are equal outside of some compact set, what we get is that when U converge to 0, being a regular value, capital U, capital G, U converges to capital G in the weak topology, but because of this equality outside of the compact sets, what we get is that capital U tilde converge in the strong topology to 1 minus lambda times capital G plus lambda times capital G. In other words, to capital G. So we have in any neighborhood of capital G, either for the weak or the strong topology, we have maps of the form capital G U tilde, okay? So that's going to be plenty useful when trying to prove the density result. But besides that, what we have is that capital EU is transverse to psi A along phi K. And what happens is that lambda is equal to 1 in a neighborhood of phi K. So this capital G U tilde are equal to a capital G U, and in particular, they are transversal to A, to psi of A, to be more precise, along phi K. So the transversality result holds for them, okay? Now, what we can consider actually, it's small g tilde, okay, which is going to be a map from M to N. We define this map in the image of U hat just like this, right? And we defined small g tilde in the complement of the image by phi of U hat as G. Okay. And again, okay, here we can consider, here we could consider U, and here U, whatever, and here again U, and the issue is that when U is a regular value that is converging to 0, this small g tilde U converge to G both in the weak and in the strong topology. So what we get is that the set of, since we can do this for any of the maps, any of the CR maps such that the image of K is containing W, what we get is that the set of such maps that satisfy that G is transverse to A along K is, we already know it is open, but it's an open and dense subset of the set of CR maps such that the image of K is containing W. And this is what we wanted to show. We just saw a local transversality result Now let us consider a global transversality theorem. Let M and N be manifolds, for instance, infinity manifolds, and let A be a closed submanifold of N. Then we have that the set of CR maps that are transverse to A along L is an open and dense subset of the space of CR maps for the strong topology if L is closed, and the same set is an open and dense subset of the space of CR maps with the weak topology if L is compact. Okay, in the second case, when L is compact, we can consider a cover of L by compact subsets that are small enough so that we can apply the local transversality theorem. And in that way, we are going to be able of writing this set down as a finite intersection of open and dense subsets of the space of CR maps with the weak topology. But a finite intersection of open and dense subsets is still open and dense. So in that way, we are going to obtain the second result. With respect to the first one, what we can consider is a locally finite cover of L by compact sets. In any one of those, we are going to apply the local theorem. And the idea is that since the cover is locally finite, that's the kind of situation that is well adapted to work with this strong topology, and we are going to obtain still a set that we are going to be able of proving that this set is still open and dense, is still an open and dense subset of the space of CR maps with the strong topology. Okay? In the following theorem, we are making the hypothesis a little bit weaker. We consider M and N manifolds, infinity manifolds, for instance, and A a submanifold of M. Here, the submanifold, in contrast with the previous theorem, is not necessarily closed. Then, the set of CR maps that are transverse to A is residual and thus dense for both the weak and the strong topologies in the space of CR maps. We have to realize that the space of CR maps with both the weak and the strong topologies is a Verse space. We proved that explicitly for the strong topology, but it is even simpler for the weak topology because such space is a complete metric space, and a complete metric space is always a Verse space. So in particular, a countable intersection of open and dense sets is always going to be dense for both the weak and the strong topology. Okay? So how can we prove this theorem? What we can do actually is we can consider A as a countable union of AKs, and AK is going to be a submanifold of N with boundary. We can also write down M as a union of MKs, okay, where MK is a compact set. And indeed, indeed we can even consider an exhaustion if we want. Now, what we have is that the set of CR maps that are transverse to A is the intersection for every K of the set of sphere maps that are transverse to AK along MK. For instance, okay, we don't even need to, we can consider here different indexes. Okay. Now it's clear. And as a consequence, since these sets over here are open and dense for both the weak and the strong topology, because this set over here is compact and the set AK is closed, then the set of sphere maps that are transverse to A is residual, and in particular, dense. Now let us consider a couple of corollaries. Let A and B be CR submanifolds of manifold M. Then any neighborhood of the inclusion of A in M in the space of CR maps from A to M with the strong topology contains an embedding that is transverse to B. Okay? But what we know is that the space of CR maps from A to M that are transverse to B is indeed a dense subset of the space of CR maps from A to M with the strong topology. Now consider N be a neighborhood of E in that space, the space of CR maps from A to M with the strong topology. Okay, since I is an embedding, there exists M prime, a neighborhood of I in the space of CR maps, again with the strong topology, such that all its elements are embeddings. This is because the property of being an embedding is an open property. Okay, but since this set over here of maps that are transverse to B is dense in the space of CR maps, what we have is that there exists E prime that belongs to such set of maps transverse to B to the neighborhood N and to the neighborhood M prime. And so we found I prime in N was any neighborhood of I such that I prime is transverse to B. Okay, and moreover, since I prime belongs to M prime, I prime is also an embedding. So I prime satisfies the properties that we need. Okay, and so in every neighborhood, we found an embedding that is transverse to B. We also have the following theorem, that it is a slight generalization of a result that we already saw. And if we have K CR submanifolds of a manifold M, the subset of CR maps that are transverse to all these submanifolds, okay, is residual in the space of CR maps with a strong topology. We saw this for just one submanifold, but the proof for a finite number of them, or even a countable number of them, is exactly the same. It's completely analogous. And so we get this result almost for free. In the last few lectures, we studied the properties of the weak and strong topology in the space of CR maps between two differentiable manifolds. And the reason is that these topologies provide the right framework to study stable or dense properties in the space of CR maps. For instance, we saw that under the right hypothesis, the space of CR maps that are transverse to a fixed submanifold is open and dense for the strong topology. In the next lectures, we are going to switch topics completely, and indeed, we are going to study vector bundles. At first, we are going to give the definition, then we are going to study some elementary properties, and little by little, we are going to study more interesting properties, and in particular, at some point, we are going to see the tubular neighborhood theorem. Thank you for your attention.